Hi, everyone. Welcome to the International Methods Colloquium. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Marc Ratkovic from Princeton University, giving a talk entitled Sparse Estimation with Uncertainty, Subgroup Analysis in Large Dimensional Designs. Marc's talk will last between 30 and 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And Marc has made a point to let me, or to have me say that if you have clarifying questions during the talk and you sort of want to just ask about something, just let me know. So type a Q&A, type a request into the Q&A box, and I'll ask it right away. A link to Marc's paper and his slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation. I'll post those right after we get started. And with that, I'd like to welcome Marc to the IMC. Marc, welcome.
Thank you, Justin. Well, first off, I'd like to thank everyone for being here today. This is a wonderful opportunity. Justin, thank you for setting this up.
You're welcome.
And as Justin mentioned, I'm here today presenting a talk on a paper entitled Sparse Estimation and Uncertainty with Application to Subgroup Analysis. The paper is joint with Dustin Tingley at Harvard. As a motivating example, when we run experiments, we know how to calculate the average treatment effect. It's the mean outcome for the treated less the mean outcome for the controlled. But we might be interested in digging into our data a little bit deeper by looking for subgroups of data for which a treatment is particularly efficacious or not. As well, we may be running experiments in which there's multiple treatments, so we may want to know if a combination of treatments has an effect. And, compounding the issue, do these combinations of treatments have an effect for different subgroups? These issues are being brought to the fore more and more in political science as we confront increasingly complex experimental designs. I'll be discussing an analysis of a conjoint analysis later, which has several different treatments being randomized and several covariates that give different subgroups. As well, in the conjoint analysis and other sorts of designs, you'll confront repeated observations, which means that the same experimental unit will give multiple outcomes. I'll be presenting a method that allows analysis of these sorts of designs. In each of these cases, what we confront are a proliferation of possible effects. What I mean by this is that by the time you just delineate every single subgroup, treatment interaction, you're left with scores, hundreds, or thousands, or even tens of thousands of different subgroups and treatment combinations that need to be considered. So we're going to present a regression-based method today that allows you to fit these models with hundreds or thousands of different covariates. We'll be focusing on an experimental analysis today, though towards the end, we'll talk about how some of this extends to observational studies. Many of the same characteristics carry through. The method we're proposing is called LASSOplus. It makes several different statistical contributions. First, it offers a weakly informative prior structure. I draw attention to this because if you have hundreds or thousands of covariates but only 50 or 100 observations, you have to identify the estimates through the prior. So we talk about, and I'll explain in a little bit later in what sense the prior structure is weakly informative. Naturally, people are concerned that their posterior inference is being driven by prior assumptions, and we go to some great length to ensure that that's not the case. Second, the method returns sparse estimates. By a sparse estimate, I mean that the method point identifies subgroups as either having a zero effect or not. A sparse estimator is an estimator that returns a point estimate of exactly zero for some set of the effects that you're considering. Third, a common problem in this literature is returning confidence intervals. As I mentioned, or as indicated by the notion of a prior structure, this is an entirely Bayesian model. As a Bayesian model, it returns a posterior estimate that may or may not achieve proper coverage. In fact, we find that it doesn't. We develop a method that takes the posterior estimates and simulates confidence intervals that are tuned to have nominal coverage, and we show in a simulation study that they perform reasonably well. Fourth, the estimator has several or two different oracle properties. It has an oracle property and it satisfies an oracle inequality. I'll explain what both of these mean later, but at the outset, what I want to clarify is why we use the oracle. The oracle, imagine you're running regression with 100 observations and 1,000 variables. The oracle knows which variables have a non-zero effect on the outcome, and it only runs OLS on the effects that are in truth non-zero. So in all the theory in this literature, the goal is to come as close to the oracle as possible, and I'll show you in a few slides what we mean by this. Now, this is not strictly a theoretical paper. There's several practical contributions that we've implemented through publicly available software in R. The software suite that we have pre-processes data. It handles, so it does this in ways useful to the applied experimentalist. It handles repeated observations by putting in random effects for different clusters, and it extends beyond the standard linear model to the probit and tobit. At this point, I'm updating the software on a near daily basis. So if you have any suggestions or you want to see something in the software, please do email and I'll let you know if it's something that's feasible. Everything is implemented in the package Sparse Reg that's joint with Dustin. Now, let me give you an idea of what I mean by an oracle. Here, this is a single draw. This is the design of the simulation that I'll be discussing a little bit later. But in this case, we have 10,000 observations and 76 variables. And you'll notice over here, there's 3 large effects that are proportioned, that have an effect size of 9. There's 3 medium-sized effects that have an effect size of 6. There's 6 small effects that have an effect size of 3. And the remainder have an effect size of 0. This is to give you an idea of the sort of model we have in mind that we're trying to fit. Now, with 10,000 observations and 76 variables, all the estimates are identified under the theory of least squares, and you'd think that this is something we can go ahead and estimate. So we do so. These are the results using OLS, using all the covariates, where the true effects are, the black line is here, it's from the previous slide. The OLS estimates are given with the red lines, and the 90% confidence interval is given with the blue lines. Now, with a 90% confidence interval, we'd expect 10% not to achieve coverage. So we'd expect 7 or 8 of the confidence intervals to not cover the true value. And if you count, you'll see that there are 8 right in here that don't cover the true value of 0. Now, it would seem that with 10,000 observations, we should be able to do pretty well. But if you ran this using OLS, you'd find statistically significant results with a large sample size that would be misleading in this area. Let's see next how the oracle does. The oracle, recall, knows that these effects are non-zero from the get-go, so it only fits OLS to these, and it ignores the remainder. Now, you'll notice, here's the point estimates, and we can't actually see the confidence intervals just because they're so narrow relative to the previous estimate. So let's go ahead and zoom in a little bit. Starting with the 0 estimates, because the oracle knows that all of these effects are in true 0, it zeroes them out. So we don't have to worry about those. And for the remaining 10 effects, it does quite well. The point estimates seem reasonably unbiased, and the confidence interval contains the true value for all of these different effects. What we want is an estimator that can come closer to the oracle than OLS, and that's exactly what we propose. Here are the results from the exact same setup that we've been using our estimator, LASSOplus, and you'll see that it recovers all of the 0 estimates down here, so it successfully ignores these, though, unlike OLS, these have a confidence interval because it doesn't know they're non-zero coming in. Then you'll see it recovers the small estimates, the medium estimates, and the large estimates fairly well. One thing I'd like to point out is that the OLS estimator is still the best. It's the minimum variance unbiased estimator. It's blue. But what we see here is that we're engaging in the bias variance trade-off to some extent. You'll see that the estimates are biased slightly towards 0, but what we get is a huge increase in efficiency. Throughout this talk, we'll be comparing how well our estimator and others do to this Oracle estimator, which is, in some real sense, the best that can be done in this sort of scenario.
Mark, I want to ask you a question that came up. So someone asked if the Oracle's knowledge machine, is the Oracle's knowledge machine or human curated?
It's a theoretical construct. So it's human, it's neither machine nor human. Imagine it's in some Platonic realm that comes in and says, the best you can do is running OLS on this subset of variables. So it's a statistical concept that's never realized, but that we try to achieve theoretically. All right. If there's a follow-up, do let me know. Before going into the proposed method, we're going to just, I just want to run through some of the previous work on uncovering heterogeneous treatment effects. Several methods have tried to identify subgroups through tree-based methods. And you'll see several of the different citations here. And they've been a popular method. Up until some recent work by Stefan Wager and Susan Athey, they've been unable to return uncertainty estimates, whereas this is a regression-based method that returns the uncertainty estimates automatically. There have been variable selection methods that have been applied to uncovering heterogeneous effects, but I hope to show you through the simulation in the talk that LASSOplus offers several theoretical and practical realized advantages over those in terms of performance. Several different methods have come along and fit complex models using ensemble methods. Ensemble methods being an average of different models in various ways. It's popular in the machine learning literature. Or Bayesian shrinkage methods. The advantage of LASSOplus over these two is that LASSOplus will actually point identify sparse models. So unlike the ensemble methods and the Bayesian shrinkage methods, it will say this is estimated to have a zero effect and this is estimated to have a non-zero effect. Let's work through a simple illustration using a single covariate. In this case, we have an outcome variable yi and a single covariate xi. We're going to assume that the sample mean of yi and xi are both zero so that we're not going to have to worry about an intercept in our regression model. And we're going to assume that xi is scaled so that its sample variance and hence sample standard deviation is 1. We'll also assume that the data are generated as y is xi beta 0, where this is the true, beta o, where this is the true effect, plus epsilon I, where epsilon I is independent of xi, it's mean 0, and it's equivariant. The question we're going to confront in this particular illustration is whether or not we should return a 0 estimate for beta 0 or not, whether or not beta hat should be 0. We focus on one dimension for two reasons. First, in one dimension, there's analytic results that I'll show you on the next few slides graphically that we can achieve in one dimension, that we can't achieve in multiple dimensions beyond 2. Second, the reason we focus on one dimension is that a lot of the same intuition carries from the one-dimensional space up to a really, really high dimensional space. So let me show you what this looks like. Here, we're going to compare all of the different estimators to OLS, which again is the baseline. Beta hat in this case is the minimizer of the residual sum of squares, so this is the least squares estimate. Along the x-axis, we're going to put OLS. Along the y-axis, we're going to put the estimator that's being considered. Now we're going to take a brief look at the LASSO estimator. The LASSO stands for Least Absolute Selection and Shrinkage Operator. To estimate the LASSO, we're going to take the residual sum of squares, but then what we're going to do is add on this lambda absolute value of beta over here, and that's putting this part on the optimization problem is what turns it into a LASSO problem. The least component comes from the fact that we're minimizing. The absolute refers to the absolute value here. And let me show you where the selection and shrinkage from LASSO comes from. So what you'll see is that for a given lambda, the LASSO estimator traces out this shape with kinks at plus or minus lambda over n minus 1 relative to OLS. And what we see are that two regions are emerging. If the least squares estimator falls within plus or minus lambda over n minus 1, the point estimate is actually zeroed out. If you run OLS outside of pathological cases, you never get a point estimate of exactly 0. Whereas if you run the lasso, you may get a point estimate of exactly 0 if the least squares estimate is sufficiently small. Now, what's the cost of this zeroing out in the lasso framework? It induces a bias. If the least squares estimate is within plus or minus lambda over n minus 1, it's zeroed out. If it's not, then it's the least squares estimate shrunk towards 0 by this range of lambda over n minus 1. Now, what happens, as you might imagine, the lasso estimator is really sensitive to how this lambda is selected. And no small part of the theoretical and estimation problems come from reasonable ways to estimate this lambda. How does this lambda affect estimation? Let's imagine we shrink lambda from lambda 0 to lambda 1. If we do so, we reduce the bias over here, but at the same time, we reduce the sparsity region. So less of the space gets zeroed out, but the bias goes away, and we see a bias sparsity trade-off emerging. In fact, we prove in our paper, and it's been proven in several earlier papers, that there's no single sequence of lambdas in n that will both be asymptotically consistent and select only the true covariates. So we need to do something else. One earlier contribution to the literature was to introduce adaptive weights. What these adaptive weights do is leave the sparsity region untouched, but the weights are introduced to be inversely related to beta, and what you'll see is it reduces the bias. So as beta grows. So what happens is we still have a sparse region, but the adaptive weights are going to say, if I think the true beta is really large, let's give it a small bias. And if I think the true beta is small, let's just go ahead and zero it out. Those were all frequentist methods that I'd just been discussing. They're normally couched in frequentist terms. Let's talk about the Bayesian lasso. The Bayesian lasso is a hierarchical model that was introduced so that the posterior mode of the model was actually a lasso problem. And here's what we get here. I put the model along the bottom. Here, y given x beta is normal x beta, and I'm just going to assume sigma squared is 1 for now for clarity of exposition. And this is a regression model where we assume that we know the true error variance is 1. Because we have this beta in here, we have to go ahead and put a prior over it. So our prior of beta given lambda is proportional to e to the negative lambda absolute value of beta. And what you'll see is this looks like a lasso problem with that absolute value in there. Now we have a lambda, so we need a prior over that lambda, and you can take any gamma prior where delta and rho are greater than 0 to fit this model. One other popular method that's been around for a few years now through some fascinating theoretical and applied contributions is the horseshoe estimator. The horseshoe estimator works in a similar framework, except it works to reduce the bias induced by the lasso, by the Bayesian lasso. So here, y is x beta, again as before. Now we're going to write beta as a scaled mixture of normals. And in this case, the prior of beta given lambda is normal 0 lambda squared. And then we put a Cauchy prior, a half Cauchy prior, over the lambda. And what this does is it goes ahead and it shrinks the bias up here, but it also encourages this to be 0. Now, one problem with all these Bayesian estimators, the Bayesian lasso and this one, is that the point estimate, the posterior mean, is never exactly 0. So I'll return to that point in just a moment. A second point with these Bayesian lasso estimators, the horseshoe estimator, the Bayesian lasso, and there's a variety of different variants that we discuss in the paper, the prior goes to 0 too quickly. What do I mean by this? We're used to the likelihood swamping the prior, and that's a good thing. That's what's supposed to happen for a fixed k as n goes to infinity. But under the standard models that exist, the prior goes to 0 too quickly. So we'll talk about our solution in just a moment. And that is the LASSOplus estimator, where we're going to work to fix both problems. First, let's take a look at the LASSOplus effect estimate. It's a similar model to what we just saw, and now we're talking about the LASSOplus estimator. Again, we have the regression component. That's a standard regression model, Bayesian regression. Here we have a prior over beta and lambda and w. Now recall the previous prior for the Bayesian lasso was e to the negative lambda absolute value of beta. What we did was actually put adaptive weights into the Bayesian hierarchy, so it's estimated endogenously. The second problem that we discussed is how the prior goes to 0 too quickly and the model converges to the least squares estimator too quickly in the earlier models. In our model, we actually introduce a prior that scales in the square root of n so that the strength of the prior persists in n. So we end up with a model so that there's some positive mass on there being a sparse estimate in the limit. The rest, the W generalized gamma and the gamma exponential 1, serve to complete the model and are there for algebraic convenience. And they're obviously necessary, but they don't drive the model. We actually played with this specification in a few different ways, and the model's robust to different values up here. So as I mentioned, the LASSOplus estimator starts with an effect estimate. And you'll see it gets close to 0 in this region, is relatively unbiased in this region. The LASSOplus estimate is actually a combination of a thresholding function and the effect estimate from the previous slide. How do we do it? We take the effect estimate, and then if the effect estimate falls within this range of this thresholding range, we go ahead and zero it out, else we leave it close, else we leave it relatively unbiased. Now, this threshold was actually developed with theoretical properties in mind, and let me show you how it performs. The LASSOplus estimate is the estimate from the last slide times S, where S is an indicator function for whether the least squares estimate falls outside of some range. And this range is scaled to grow as n to the 1/4. Let me show you what this achieves. For folks familiar, this is actually reminiscent of Hodge's estimator. So let's take a look at the asymptotic behavior of LASSOplus, in which the true effect is 0. So now we're going to assume that beta is in truth 0, and we're going to let n grow and see what happens to the thresholding region. If beta is in truth 0, the thresholding region is going to grow to encompass the entire real line. So as n grows, if it's in truth 0, we zero it out. Now let's assume beta is not 0. In this case, if beta is not 0, as n grows, the thresholding region shrinks so that we will never zero it out. And we develop this thresholding region such to correctly differentiate, at least in the limit in n, the in-truth 0 effects from the in-truth non-zero effects. Let's talk for just a moment about the tail behavior of LASSOplus. As I mentioned, folks who use Bayesian models are understandably concerned that their posterior results are driven by prior assumptions. To some extent, they're going to be, but we want to minimize this. So how do we do that? Here's a figure of the prior density for a variety of different methods on a log scale on the y-axis versus the absolute value of beta on the x-axis. Here you'll see the normal prior is quadratic down because it's proportional to e to the negative beta squared. So it's quadratic down. The lasso estimator's right here, and it's proportional to, the log of it is linear, negative absolute value of beta, so it goes down like this. What you'll notice is that the normal prior doesn't actually have a spike at 0 because it doesn't give a positive posterior mass of achieving a value of 0. This is different from the horseshoe prior and the LASSOplus prior. The horseshoe prior is this dashed line, which both spike up at 0. So what we're saying through our prior is we really think, walking in before looking at the data, some of the effects are going to be exactly 0. The other question is, if the effects are large, do we want our posterior estimate to be affected? The answer is probably not. So what we do is, if beta gets large, we actually want the largest tail mass that we can get. And what you see here is that the LASSOplus prior achieves a thicker tail, has a fatter tail over here, than both the Cauchy prior, which is this dotted line, and the horseshoe prior, which is this dashed line. So what this is saying is that for large values of beta, posterior estimate is less affected by the prior assumptions than these other estimators. A standard measure of the influence of a prior on the estimate is the entropy. Here is the entropy of LASSOplus, which is 5 point. The higher the entropy, the less the prior is informing the outcome, informing the inference. The LASSOplus prior has an entropy of 5.57, which is larger than the normal, the Cauchy, the lasso, and the horseshoe. There's an extra gamma parameter, which was introduced in the model, and what this is going to do is actually, after seeing the data, this gamma is going to adapt to the global sparsity estimated from the model. And you see that this gamma parameter, if we range it from 0.25 to 2, actually gives different levels of entropy to the prior itself. Question?
Mark,
Yeah.
before you get too far into that, we have a question about the previous slide, the tail behavior slide. So how does this visual change as a function of different subgroups?
Oh, as a function of different subgroups. Absolutely. We're still sticking within the one parameter case for exposition. With different subgroups, it actually will be the same. It will be the same up to a scale parameter, so it'll shift up or down perhaps for different subgroups. It'll shift up or down for different subgroups, but the relevant performance of each of these different priors will stay the same.
Mm-hmm.
So we were talking briefly about this gamma parameter, which serves to adapt to the global level of sparsity as estimated in the data. And gamma is estimated endogenously, and as gamma changes, we see that it really affects the tail behavior of the prior. To put it down and to come back to the earlier question about what happens for different subgroups, the answer is actually embedded in this slide because now we're in a multivariate world. In this multivariate world, now we're going to assume that y given x, beta, and sigma squared is a normal Bayesian regression. Each individual beta k given lambda, sigma squared, and the weights looks like an adaptive lasso, the wk times lambda over sigma within this absolute value. And if the beta k's are indexed for subgroups, the prior is still going to look like an adaptive lasso. The wk given gamma is going to have this generalized gamma form, and gamma is going to be exponential 1. So one thing I want to emphasize is in these Bayesian models, at some point you have to stop putting layers of prior on things. Otherwise, it's just turtles all the way down. And what we do is we stop the decisions that the researcher has to make is this 1 over this gamma. That's the one that's not pegged by our model. It turns out the generalized gamma, these terms are pegged and we justify them in the paper theoretically. This exponential 1 is not. And we've gone ahead and tried this, setting this to 1/2, 1, and 2, and 3, and we get basically the same results. This gamma is a, let's see, this is a prior, hyper-prior. This is our hyper-prior parameter. And it's well known in the Bayesian literature that the further down in the hierarchy the prior is set, the less influence it has on inference. Now, as I mentioned, we go ahead and we calibrate the prior by sample size to have desirable theoretical properties. Now, I want to make it clear that we calibrate this prior so it has desirable frequentist properties. What folks have done is come to this prior and set the prior as, say, gamma 5,7 or something like that. What we did was we went to the frequentist literature and said, given the results from the theoretical literature over here, how can we integrate this into our prior, because it is prior knowledge. So here we see that the beta given lambda, wk, and sigma is doubly exponential lambda, wk over sigma, which was from the previous slide. Here's the part where we calibrate by sample size. I see a question, so I'll pause for just a moment.
Yeah, so the question is, given the interest in tail behavior, is the gen gamma parameter assumption informed at all by estimation of a tail index? For example, by using Pickens, Hills, or Gabai's OLS log rank methods?
Huh. Well, whoever asked that question, if you could send me that citation, I'm all of a sudden really interested in reading it. But on the spot online, completely unable to address that particular citation. What I will tell you is that we constructed, and we described this in the paper, and I'd love to continue this conversation either in the Q&A or offline. This generalized gamma, this generalized gamma is constructed such that the log posterior of this model looks like, is actually algebraically equivalent to the adaptive lasso problem as introduced by Hui Zhao in 2006. So that's where we get the structure for this generalized gamma. We do it so that it exactly matches up with this earlier paper by Hui Zhao. As to the particular paper and reference that you mentioned, I'd be glad to take a look at it. We were more informed by the literature on objective Bayesian priors. So the priors calibrated, we discussed how this k term in the square root of n minus 1 in the prior on lambda is going to sort of slow down the rate at which the effect of the prior goes to 0 in sample size, and that's going to give us some desirable theoretical properties. One other thing we do is actually estimate approximate confidence intervals. So the approximate confidence interval, we go ahead and apply the delta method to an approximation of the point of the LASSOplus estimator. This is outlined in the paper, and we actually implement a method by Brad Efron in the 2015 JRSSB. Now, the delta method is going to give us reasonable coverage, but it's a normal approximation. So what we do is we go ahead and we use Satterthwaite's approximation to make the small n corrections that we're approximating using an approximate t-distribution rather than approximate normal. And we find that this has an effect at the smallest sample sizes. Given the delta method and Satterthwaite's approximation, we then use a Bonferroni correction for discovered effects in order to account for the fact that we've discovered multiple results. And we discuss we discuss the details of this in the paper, but I'd be glad to go into it in some of the Q&A. One other thing is that we want this method to be useful to the applied researcher. So we go ahead and we implement it using a latent probit model, using the standard Bayesian latent probit formulation. And we implement random effects for repeated observations. The software handles up to 3-way random effects. We can fit it via Markov chain Monte Carlo or via EM. Everything's done in the package. Now, we have 2 statistical properties that I want to discuss. The first is an asymptotic condition on the oracle property, as it has 2 different components. First, as n goes to infinity, it selects the true model. Second, as n goes to infinity, it's statistically indistinguishable, i.e. converges in distribution, to OLS fit to the true subset model. For this to work for our model, we require k squared over n to go to 0, which means for a k of 10, for 10 covariates, you need approximately 100 observations. This is an improvement over k to the 5th over n, which was discovered by Fan and Peng 2004, where for 10 covariates you need about 100,000 observations. Where do the gains come from? In this earlier paper, Fan and Peng look at general likelihoods and general penalties, whereas we're looking at OLS with a very specific penalty, so we're able to sharpen this bound for our model. Next, we look at the oracle inequality, which is a predictive property. If you'll notice, with k squared over n going to 0, this simply will not work if k is growing faster than n, or if k is larger than n. So if k is larger than n, we can't get the right model. But if k is larger than n, what can we do? Well, we can get the right predictions, or we can come close to the right predictions. And that's what the oracle inequality is going to give us. We're going to assume the true subset model is in truth sparse and full rank. And for a sufficiently large k, we're able to bound how close our fitted values are to those from the true or subset model, or from the oracle itself. To go into a simulation, we ran a simulation as if it were a conjoint analysis from sample sizes 50 to 2,500, 3 different treatments. First had 2 conditions, the second had 3, the third had 4, all equiprobable. The number of moderators ranged from 10 to 100. Then once we saturate the model with interaction terms, we end up with between 76 and 706 possible effects. We're going to go ahead and focus on the 76 and 706 possible effects. The rest of the results are in the paper, but basically the results sort of gradate from here to here. We have three different sets of effects. We have three main effects on the moderators, which generally we're not interested in a normal study. Then we have three main effects, which are main effects on the treatment, which may or may not be of interest. But what we're most interested in are these 6 smaller effects. These are where we can really add nuance to our underlying theory. Everything is scaled so the true R squared is 0.5, and we got this from the example that we're about to run where the fitted values gave us an R squared of about 0.5, and we have T5 error. Now, what we're going to do is see how well our method does by 3 different measures. How many false positives does it make? How many false negatives does it make? And what's the false discovery rate? The false positives are how many in-truth non-zeros does it identify? The false negatives are, in-truth zeros does it identify as non-zero? The false negatives ask how many in-truth non-zeros does it identify as 0? And the false discovery rate says of all the estimated non-zero effects, what proportion are wrong? As I mentioned, we're looking at 76 possible effects and 706 possible effects. And the sample size is along the x-axis. What you'll see is that LASSOplus, relative to the other methods, achieves a lower false positive rate, and at 76 observations achieves a reasonable false negative rate. It's less aggressive than many methods. But really in this world, what we're interested in is the false discovery rate. What proportion of uncovered effects are in truth false? This is normally what we want to minimize. And what you'll see is that the LASSOplus, relative to the other ones in red, achieves a low false discovery rate. Those same results hold at 706 possible effects, where it achieves a low false positive rate, so it's a conservative estimate. It misses quite a few. It's not aggressive in identifying false negatives, but it manages to balance it well in the false discovery rate, achieving a really low false discovery rate here. As I mentioned, the previous figure looked at all the effects, the 3 large main effects, the 3 large treatment effects, and the 6 interaction terms. What we're really interested in are the interaction terms, though. Those are the ones that add real nuance to our theories. We see a same pattern here for the interaction terms that we do on the previous slide. Low false positive for us, some false negatives, it's less aggressive in terms of identifying effects. But let's take a look at the false discovery rate for K of 76 and K of 706. Let's assume we have N of 500 and a K of 76, which you'd think would be something that we can estimate. Other methods of the identified effects, between 40% and 75% of the small effects that are recovered using these other methods will be in truth 0. That's what we find in our simulations, whereas at N of 500, for us, it's about 0.1. What we're saying is that for for small effects, if we find one, odds are pretty decent it's actually there. For 706 effects, LASSOplus doesn't actually estimate a small effect until the sample size of 1,000. So if you have a regression with 706 variables and 1,000 observations and 100 observations, LASSOplus is going to come along and say, don't look at these small effects. We don't trust that they're there. We mentioned coverage on the earlier slide. Here's a comparison of coverage across different methods. This 90% line is nominal coverage. And you'll see that LASSOplus, again in red, does reasonably well. For the most part, above 250, it stays above 0.8 in terms of achieving coverage. And for 706 effects, it also hops around 0.9, achieving close to reasonable coverage. Now, in the last few minutes, I just want to go through an application. Bechtel and Chivy did a study on the effect of the design of international treaty design on support for a treaty on climate control. The Conjoint experiment was run across 4 different countries, and the treatment conditions were the cost of the treaty, the proportion of the extent that other countries are participating, the extent of the sanctions, and who monitored. We did this with 250 total effects. There were 31 main effects and 184 treatment covariate interactions. The original study investigated subgroup effects by multiple split sample analyses. First, I want to show you the results from the original study using the C-joint package, the Conjoint package in R. I want to highlight two results just to establish some validity. First, as the cost of the treaty increases from $53 down to $267, you see that the support for it wanes, which is to be expected. Second, as the number of countries participating increases from 20 to 160, the support increases, both to be expected. Now let's see how that compares to the LASSOplus estimates, and these are the results from our software. You'll see a similar result. As the cost goes from $53 to $267, the estimated effect goes down, as to be expected. And as the countries participating goes from 20 to 80, which is zeroed out, to 160, you see the effect size goes up, which is what we want. The advantage of LASSOplus is we can recover these same effects that you get from the conjoint analysis, but it also returns interaction effects. It returned a fair number of interaction effects. This is the complete list, but what we're going to do is focus in on two particular results: the interaction between conservative and who's doing the monitoring. So we're going to focus in on these two effects here. And these are all figures that come straight out of our software. Most of these analyses can be implemented in just 1 or 2 lines of code. What you'll see is that the conservative times Greenpeace interaction, conservatives don't care for international treaties. Greenpeace, they don't care for Greenpeace monitoring, but if conservatives are exposed to the Greenpeace treatment condition, we see that there's an extra additive negative effect. If they're exposed to the UN monitoring, it's 0 with some non-zero posterior density here. And if the conservatives are are told your own government's going to do the monitoring, then they prefer that relative to Greenpeace doing the monitoring. That struck us as reasonable results. So in conclusion, LASSOplus is an estimator that possesses the oracle property and satisfies an oracle inequality. We showed through a simulation it achieves a low false discovery rate. It does a reasonable job at identifying non-zero effects and returns approximate confidence intervals. Some ongoing work that we were working on today, estimating treatment effects, extending it to instrumental variables, mediation models, and also extending it to observational data. Everything that we presented is available in an R package, Sparse Reg. It's being updated regularly. And if you have any questions, please let me know either now or via email. Thank you.
Okay. Thank you, Marc, for that presentation. At this point, Marc Ratkovic is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And while we're waiting for some questions that come in, so one thing I've heard, one criticism I guess I've heard leveled against Lasso as an idea is that there's no such thing as a zero effect, right? So in a simulation where you set certain effects to be 0, Lasso does better, but in real data, everything's related to everything. And so you're essentially forcing bias into your results. What do you think about that?
There's a few different parts to that response. The first part of that is when we run analyses, when we run a linear regression, we run the regression and then we compare our estimates to their precision, and we get a t-statistic and a p-value, and what we want to know is which ones can we differentiate from 0 and which ones can't we. So technically what we're doing is not assuming that some are in truth 0 and some aren't. What we're trying to answer is a different question. Which of these effects can we reliably separate from 0, distinguish from 0, and which ones can't we? Now, in fact, as I mentioned, the LASSOplus estimator is based off of an effect estimate times a threshold. The effect estimate is never actually sparse. It never returns a point estimate of exactly 0. It's a Bayesian estimate that shrinks to 0 but never gets exactly there. If you're interested in identifying effects, I recommend the LASSOplus estimator because it gives a principled means of selecting which ones are 0 and which ones aren't, and this is closer to inference. If you're interested in something like prediction, I recommend leaving all the effects in because, just as you point out, it's probably not exactly 0. In the paper, I go to some length to never say it's exactly 0, but to go ahead and say these effects are negligible or relevant. And that's the way I like to think about it. How big is the estimated size relative to the sigma over the square root of n? So we're not saying it's exactly 0. There are theoretical results for the oracle inequality that do require assuming the model's intrude sparse, and I highlighted those in the slide. But all of the theoretical properties for LASSOplus, because it's a Bayesian model, don't rely on that assumption.
So if the question is one of inference,
yes,
then there are other alternatives, right? We could use the Benjaminian-Hochberg procedure to
yep.
sort of adjust the confidence intervals or tests if you're doing actual tests.
Yep.
In fact, this ain't my talk, but to plug my own work, I've actually done a little stuff with that in interaction terms. So why is it that Lasso you would expect, or LASSOplus in your case, why would you expect that to work better than just sort of adjusting the confidence intervals?
We actually rely on the Benjaminian-Hochberg work when we do the Bonferroni correction, because we do a Bonferroni correction off the discovered effects to get correction, to correct for the multiple testing problem. And Benjamini has a JASA paper that we cite, that we talk about, that implements this. Mm-hmm. Now, in terms of what you're doing, I would like to point out that we have this software. There's other software that does that. Any good applied research or experimental study involves running multiple things.
Of course.
Right? I'm not proselytizing this at the expense of everything else. But the Benjaminian-Hochberg approach does rely on some sort of least squares type estimation underlying it. And as I showed you on the first couple slides, if the effects are set up so that some are large and many of them are small or close to 0, we can use this Bayesian prior to engage in the bias variance trade-off to some big effect. So I think in applied studies, this might work better. And if it does, send me an email so I know that. But both are valid. They're just different sets of frameworks. One other thing I'd point out is that our framework extends to the probit model and handles multiple observations, repeated observations, neither of which is straightforward to implement, the probit, tobit, and random effects. And none of those are straightforward to implement in the Benjaminian-Hochberg framework that you're suggesting.
So we have a question from Pete Mohanty, who's actually next week's speaker.
Oh, great.
As you see it, what would be the main obstacle or obstacles in adapting this technique to the observational setting?
Oh, thank you, Pete. Great question. Because that's exactly what we're working on now. This study actually came about for, among other reasons, for use in an observational study. But we couched this largely in an experimental framework, so that we didn't have to debate whether or not the estimated effects were causal. By definition, we don't have to worry about confounders, and we don't have to worry about unobserved variables because we randomized. This is a paper that says if you don't have unobserved confounders, you can go ahead and estimate all these things. In an observational study, there's two types of missing variable problems in a regression. The first type of missing variable problem is you're missing a variable that's constructed from the variables that you have. An interaction term, a square root term, a spline term, something like that. The second type of missing variable problem is you're just missing something that's totally unrelated to what you observed. We're focusing on that first problem. In an observational study, can we fit a model with all the main effects and all the interaction terms, or take an index like polity and decompose it into different components and fit regressions with hundreds or thousands of variables instead of 5 or 10 or 20, and try and figure out what's going on in our data with some more fine-grained nuance? The second question is, if there's an unobserved confounder that is independent of what you observed, but affects the outcome, this method can't help there. In fact, nothing can. Go find that unobserved confounder and proxy for it. But we focus more on that first part. A lot of these basic ideas do carry through directly to observational studies, with the caveat that all of the problems that come with regressions and observational studies also carry through.
Well, it's following up on that question.
Please.
A lot of there's been a big push, and you can see it in syllabi for graduate education. You can probably see it in the reviews that you're receiving now. There's been a big push toward in observational research some sort of identification strategy, and there are many different sort of ways you can approach that.
Yep.
Is this technique, because lasso is kind of interesting in the sense that it belongs to a family of techniques that are really about trying to let the data say things, right?
Absolutely.
About trying to let the data tell you what's there as opposed to testing a theory. And you can certainly use it for that purpose, but it's informed by letting the data kind of speak. Yeah. Is this technique, and is lasso in general, compatible with having an identification strategy as that's typically defined in observational data?
Absolutely. Absolutely. What the way I think of this, and I hope people will adopt it, is as a better regression. So you may fit a regression with all main effects, and there's nothing wrong with that. We've been doing it for decades and learned quite a bit. But at that point, you're the one doing variable selection because you're not putting in all the interaction terms. You're effectively zeroing them out. Mm-hmm. You're making linearity assumptions that may or may not be accurate and may have some impact on your results. Now, if a causal effect is identified in your strat, the question of whether or not a causal effect is identified in your data and identified in your study and in your design is a different question than how do I estimate that causal effect. We've had a lot of great work on how do we identify these causal effects. What assumptions do we need to get controlled direct effects, to get mediation effects, to get instrumental variable effects, to get regression discontinuity effects, all these different things. We've put a lot of work into identifying them. I'm focusing on an orthogonal question. Given that it's identified, at some point you have to put your data up against them. You have to put your data in a computer and actually look at what the results and estimate results. And I'm focusing on the question of estimation. All of the identification assumes you have the model right in order to get the right result, or that's not entirely true. But it does require having a reasonable model for a fair number of identification results. What we're doing is saying, well, let's work on that part where we can get a better model.
Well, so if your strategy is conditioning on all confounders, then yeah, I mean, that makes sense. What if my strategy is, for example, having an instrument, right, which is a common alternative?
Absolutely, and that's something that we're actually working on that now. One way to think about it in the instrumental variables case is this: you'd fit it through two-stage least squares, right? I mean, I'm presuming, or let's just say two-stage least squares, right?
That's certainly the most common technique, yeah.
We have an instrument, we have an endogenous variable. Mm-hmm. One of the problems with that, there's a few different problems with that sort of approach. One of them is obviously the modeling assumptions that you're making right there. If I have an instrument, then that instrument times X is also an instrument, mm-hmm. right? But people don't do that. Why? Because no one trusts the model with all the interaction terms. So I'm coming back and looking at it that way. A second problem with instrumental variable analysis, and this is well understood, is that the causal effects are valid only on a subset of the data that's impacted by the instrument. That's what the local average treatment effect refers to. Now, what this method can allow you to do at the first stage is actually find out which subsets of the data are impacted by the instrument. By looking at it, doing a subgroup analysis in the first stage, you can see where you're estimating an effect between the instrument and the endogenous variable. Much of the same intuition carries through, but what we're allowing for is a more fine-grained analysis of existing modes of estimation.
We have time for one more question. Lots of MCMC folks are switching to Stan for speed. Yep. Do you see yourself going in that direction? And if so, why? And if not, why not?
At this point, I was unable to code this up in Stan because of the particular prior structure that I have. Putting the sample size and the covariates, and at least with this software, it's just easier for me to code it up on my own. It is coded up in RCPP, so the bulk of the work is done in C++, so it is effective. But I'd be glad to have an online conversation about how to put some of this in STAN. I will say that I've compared this method at some length in the paper and outside to the horseshoe estimator, which is now implemented automatically in STAN and has a nice, wonderful instrument implementation in RSTAN ARM, a package. Very easy to implement. And I find time and time again that this method outperforms that one, both in terms of prediction and variable selection. I would love to be able to sync it up with the STAN community. I just haven't sat down and done so. And I think the software offers a sufficiently encouraging performance that that's a conversation I'd love to have, because that would make this easier to implement when it comes to other limited dependent variables rather than having to code up bespoke samplers.
Okay, well, that's all the time we have for this week's IMC. Next week, November 11th at noon Eastern, we will host a talk by Pete Mohanty of Stanford University. He's going to give a talk on joint work with Robert Schaefer entitled Messy Data, Robust Inference, Navigating Obstacles to Inference with Big KRLS. Please see our website, www.methods-colloquium.com, to get more information about this talk and the rest of our schedule for the 2016-2017 academic year. Marc, thanks a lot for your talk today. I really enjoyed it.
Thank you, Justin. I'd like to thank everyone for watching.
Yeah, and I hope to see you next week.
Fantastic. Thanks.